Should I just kind of should we represent it from the beginning? I think probably. Okay, cool, awesome. Okay, well, we've had a few technical difficulties. Apologies for the lack of audio. We realized that the computer audio wasn't being connected, so I think you heard my introduction, but you didn't get you weren't able to hear a full draw. So I think the introductions has come through. So I'll hand over to you now. Full draw. We can start again, but again, really great to have you with us.
Okay. So I can restart my presentation, right?
Yes, thank you.
Okay. Yeah. Thank you, Daniel. And today I will present our work, OpenMoE, an early thought on open mixture of expert language models. And okay, so first for the background, what is transformer? Transformer is a neural network architecture. I think it's very well known, as widely used on so many applications, including ChatGPT. The T is ChatGPT is a transformer, right? So a transformer model architecture includes many transformer blocks, and each transformer block include a few layers like multi-head attention, feed-forward neural network, and a few tricks like layer normalization and residual connection. So basically, transformer is a neural network architecture. And so what is MoE? So today we mainly focus on the MoE on transformer. So basically, MoE. So far, so-called MoE is a transformer modification. We replace the FF layer by the MoE layer, and in this figure we can see if we are using a vanilla transformer, we should have self-attention, add plus normalize, FF layer, and add plus normalize. And for for speech transformer or for MoE based transformer, we replace the FF layer by speech FF layer, which is also named as MoE layer. And in each MoE layer, we include many parallelized. Sorry, systems by saying no sound.
There's still no sound again. What's going on? Has OBE done like an update that's made everything break? No, I can hear the sound.
Yeah, it's audible. Yeah.
Yeah, I think there is sound. Okay. I just quickly opened up the YouTube and I can hear sound. So I guess I don't know what's going wrong on your side, Joe. But hopefully it works if you kind of stream the YouTube yet. Okay. Anyway, sorry. Full draw again. We'll stop interrupting you. Feel free to keep going.
Oh, okay. I can keep going now.
Yeah.
Okay. So, okay. This is the MoE layer. We select only a few experts for each token adaptively. So basically, it's an adaptive sparsely activating of the expert selection. So okay, then let's go back to the history of mixture of experts. The history of experts can be traced back to very long ago, and one milestone of MoE-based neural network can be tracked to 2017, when the Hindus team proposed one LSTM plus MoE model architecture, inserting MoE layer into the recurrent neural network. We can see in this figure that the MoE layer here has been very similar to the MoE-based transformers MoE layer, right? It's basically activating the sparse expert adaptively. So after that, Google proposed G-Shard. G-Shard is a MoE machine learning system for MoE-based transformer. You know, the MoE-based transformer is activating the parameters sparsely. So it's a sparse neural network, not that parameter efficient. So and transformer is memory intense neural network architecture requiring a lot of GPU memory. So to train the transformer efficiently, people proposed expert parallelism. That is, they only keep one expert on each GPU, and when routing the token representations to different experts, they conduct all-to-all communications. This is a G-shard machine learning system implemented. Okay, then after that, the Google also proposed speech transformer, different from G-shard focusing on ML6 or ML infra. Speech transformer focus on the transformer scaling, the algorithm was model scaling up. Here, this successfully scaled the MoE transformer to over 1 trillion parameters and actually decent pre-training and downstream performance than the dense counterpart. This is a milestone of MoE transformer showing the effectiveness of MoE transformer scaling ability.
Quick question. What's the kind of ratio in terms of weight compared to, I mean, maybe this should be obvious, but what's the size of the weights of the fully connected feed-forward networks versus the self-attention layer, like as a rough ratio? Is most of the capacity in the network, the fully connected networks, or is most of the capacity in the self-attention?
No, actually, most of the parameters, even if we are using the dense transformer, I mean, not the MoE-based transformer, most computation and parameters are in the, I think more computation and parameters are in the FFN layer instead of attention layer. So, and when we are using MoE-based transformer, the FFN layers would be more heavy than the dense counterpart, and yeah.
Okay, so sorry. The the feed-forward networks without MoE, in a world without MoE, sorry, the feed-forward networks, did you say, sorry, are bigger than the self-attention layer?
Especially on the larger scale.
Yeah. Okay. Thought so.
Okay. Okay. So there are also many follow-up works like GLAM, STMoE to improve the transformer, improve the MoE-based transformer step by step. I collected these models on my GitHub repo, also a mixture of experts. If you're interested in that, feel free to take a read. I also selected around 8 or 9 my favorite papers. I think there are the milestones of MoE research. And okay, for our work, less than 1 year ago, we proposed OpenMoE, a family of open source MoE models. OpenMoE is the first open source GPT-scale LLM. Let me briefly introduce the logo here. There are 3 different animals, right? Different animals have different jobs, and so that they are different experts. And the middle one is a line, which is a flag, is a logo of Singapore and the AOS. Yeah. Yeah, so this line is also a student. So it's because we are academic research lab from the school. Yeah. And okay, so let's introduce our OpenMoE step by step. Everything is from the data, and every amazing thing is happening because of the data. So let me see. Let's discuss the data first. When designing our data mixture, we think code is super important for 2 reasons. First, many empirical results show that code may be helpful to improve the reasoning ability and also some other abilities. And more importantly, we think code is the language of machine. You know, the natural language is sometimes blurry. Some different people, when reading a book, different people have different understandings. But for the code, when we read the code repeatedly, the code, if we ignore the random seeds, the code will usually have the same results. So it's very precise and it's stable to run. So it can be a more effective and efficient language of machine. We think the code may enable the future applications like embodied AI also. And so we think we increase the code ratio in the training data mixture, and we use a very aggressive code code data usage up to 50% code in the data mixture. And we found, actually, we found that it's a bit too aggressive. And we switched back to around 20% after 500 billion tokens, 800 billion tokens. And after training OpenMoE base and OpenMoE 8 billion for our largest model, OpenMoE 34 billion, we rethink our data mixture and think maybe the 50% is too aggressive. And we observed the performance on text benchmarks and code benchmarks. We found, okay, the 20% is a bit too weak. So we decided to use a middle point around 30% data code in the data mixture. That is our version 3. We think that maybe close to the optimal code usage in the pre-training data. And for the model architecture, we heavily followed the STMOE because it's very stable to train, and the stability is a big issue with scaling the model up. And we apply some tricks like router Z loss, follow the design, root residual MOE design, and also use the token choice routing. But the difference is we are a decoder-only MOE architecture instead of an encoder-decoder architecture. So we are GPT style model, they are T-file style model. So this part is different. Also, we made some minimal modifications, like we use a different activation function in FFN layer. We use rope position embedding instead of relative position embedding to support easier interpolation in the future. Yeah. And for the training objective, we different from most open source language models like Llama using vanilla less token prediction or causal language modeling. We use UL2 training objective, which can be seen as kind of the combination of vanilla next token prediction and mass token prediction. So the motivation of using UL2 are twofold. First, UL2 is very famous, and it was also used in Pathway language model too. It's an advanced training objective. We want to see whether it really works. And second, we use much more data than others, right? And we use much more coding data than others. And for the code, we usually work on code by filling in the middle or mask code prediction. For instance, we do some code fix, filling in some functions. So the span corruption, or so-called mass token prediction, aligns better with code. That's another reason we applied UL2 in our training objective. And we found UL2 can indeed make the model learn faster at the early stage, but it's easier to saturate. We will introduce this later. It's good, but not perfect. And for the tokenizer, we used larger vocabs than the baseline models like Llama on GPT-3. For two reasons. First, larger vocab means we can support low resource language better. So it has the potential to handle many low resource language better than other baselines, than other tokenizers. And we also hope it can model the code better because it can support more diverse tokens. And for our configurations, we mainly train 3 models. The base MOE is very small, including around 500 million trainable parameters. It's just for debug purpose. And for the 8 billion MOE, it's the model we are really focused on. We train it with over 1 trillion tokens. And for the largest one, 34 billion MOE, we don't have that much computing resource to train it until the end, but we train a larger model to verify the scalability of our model, whether our model can be scaled well whether everything is going well when we increase the model size. So, okay. Before scaling up, we conduct a set of application study to check the effectiveness of different designs like MoE, UL2, code data. We found MoE is working well, UL2 is also very helpful, and amazingly, surprisingly, code data, even if we use the more code data in our training data mixture, our model is still performs better than the baseline without that much code data on the text-only benchmark. This is very counterintuitive. But yeah, this is indeed our observation. And last, we also evaluate the tokenizer. We use the UMT file instead of Llama tokenizer. And we found actually Llama tokenizer is slightly better than UMT file tokenizer. But since we think that from a long-term view, supporting low resource language is super important for the fairness of AI because we are calling large language model foundation model, right? The foundation model should support fair service to everyone. But we think it's necessary and meaningful as a research project to study the large vocab size for low resource language. And another application study is we visualize the validation loss on different data source. So we can see our model actually better validation loss, lower validation loss on code data. This is very interesting in my opinion. We suggest the reason is low resource code data token are more long tail distributed. I mean, there are more special tokens like slash, like white space, like inter, new line in the code data. So these kind of tokens are easier to predict so that we can actually lower loss easier. We can actually lower loss on code data easier than the text data. And okay, scaling up. We plot the scaling curve. You can see we first treat the blue line. It's a small model, and it goes very smooth. And then we scale it up to the orange line, the 8 billion model. And after, because there is a big accuracy drop at the later stage of training, around 800 billion tokens. That is because we changed the training objective. You can see if we zoom the figure in, you can see there is a saturate. There is saturate phenomenon at around 800 billion tokens. We suggest the reason is first, the code data is easier as we observed just now. And second, UL2 is also an easier objective. We are providing more information instead of masking the whole sequence autoregressively. So we switch back to causal language modeling, and there is a significant accuracy drop, and the model can still improve. So we think this design is reasonable and makes sense. We are kind of setting up curriculum for the large language model training from easy to hard. So we still follow this setting when scaling up to the 34B parameters, the green line. And we can see the after warm up, but because we observed the saturation of UL2 training objective, so we only use the UL2 and UL2 during the warm up and switch back to the causal language modeling after that. And we can see for the largest model, it can actually higher pre-training token prediction accuracy than the origin line, even if it was trained by much fewer tokens. And okay, evaluation. I think we evaluate our model on many different benchmarks, including trivial QA. We can see OpenMoE is better than baselines, although we are trained by only around 50% or 60% training flops. And the OpenMoE 34B is also comparable with the OpenMoE 8B, although it was only trained by 200 billion tokens instead of over 1 trillion tokens. And similar observation on the code benchmark human eval. And also, interestingly, we conduct experiments on the multilingual, low resource multilingual machine translation. Um, Please note that we didn't use more multilingual tokens than baselines, but because of our multilingual tokenizer, the large tokenizer, you can see OpenMoE is actually better translation recalls than the baselines, although they are much fewer. They're only comparable multilingual tokens. So it's showing that the large vocab size supporting multilingual tokens indeed working to some extent. And also we compare with some Google's in-house MoE models like Big G Sparse and also OpenAI's smaller scale GPT-3. We can see OpenMoE actually better trade effectiveness cost trade-off than the baselines on the curve. Okay, another super important applications of large language model is chatbot. Just like ChatGPT, right? It is a game-changing product of OpenAI built on the GPT-3 models. And evaluating chat models is then very important. And we conduct our experiments on MT Bench, one of the most popular and well-known chatbot benchmark. We can see our model is better than the baseline. On the left figure, our model is significantly better than the baselines across many domains, many tasks. But as a right figure, our model is not that good. So why does this happen? We will explain this a few slides later, and let's keep it. I hold the problem here. This table can show the results more clearly. We can see in the first turn, OpenMoE is the best, and in the second turn, OpenLlama is better than OpenMoE, and in average, we are comparable with OpenLlama and better than other baselines. So then the question is why there is a so significant performance drop at the second turn. There probably some bug or some wrong inductive bias, right? So why? To dive into the weakness, or we conduct a set of visualization on OpenMoE models to study the MoE's behavior. Actually, I think the MoE's research community is a bit weird. Not the MoE, because of the GPT's false leak. OpenMoE is so MoE's research is so popular, and everyone is talking about MoE, but few people talking few people talk about what are the experts specializing at, what are the experts good at, and why tokens are routed to the experts. So to have some insights on this problem, we conduct the visualizations like this. We first visualize expert selection decisions on different on the data from different subsites. In this plot, we have 32 expert. E0 denotes expert expert 0. E1 denotes expert 1. So there are 32 experts in total, and we can see the tokens from different data sets are uniform, almost uniform distributed across different experts, right? And there are a few interesting observations, like both GitHub and Stack Exchange data prefers expert 21. And another thing is much fewer tokens selected expert 0 and expert 1. We will explain these two observations a few slides later. And also we visualize MoE specialization in language level. We can see in the left figure, we compare different code language. It's still there is still no significant expert specialization. At the right figure, we compare different natural languages. We also observe some interesting specializations, like simplified Chinese language and traditional Chinese language both prefer expert file. That means similar language prefer similar experts, but not that clear. We can observe some insights to some extent, but it's not absolutely a specialization. And from the task level, writing, role play, reasoning, math, coding, we found some math and coding prefer expert 21 again, but yeah, there's still no clear insights when seeing this plot. Then we also visualize the position ID, but still no significant observation, no clear specialization on the plots.
Is this the position ID of the token in the sequence?
Yes.
Okay.
Okay. Yeah, and then this figure is becoming very interesting and maybe the most important figure in the OpenMoE project. We plot the token selection, the expert selection decision for each token ID, and select a few token IDs from our routing decisions. And in this figure, we can see the specialization is super clear, and almost all tokens ED selected expert 30, and almost all tokens AN selected experts 24. And you know, different ED tokens have different prefix and suffix, have different contexts. Like ED can be a suffix of care, can be a prefix of education. AN can be the prefix of another, can be a prefix of an apple, an elephant. So the contexts can be very, very different, but these tokens are always are always dispatched to the fixed expert. So we call it context-independent specialization.
Quick question.
And
Sorry, quick question.
okay.
So these mixture of experts, how many places do they appear in the broader LLM? Are there several? Are there kind of several of these? Sorry, my headphones just came out. Are there several of these mixture of experts stacked together?
No. We actually select one MoE layer from the OpenMoE model, but we didn't observe significant difference across different MoE layers.
So
For instance,
even like very, very deep into the model where the initial token has gone
yes,
through many, many layers of like representation, very
yes,
deep into the model, you still see this sharp specialization.
yes.
Wow.
Yeah,
Crazy.
yeah. I visualize the area MoE layer, and
Yeah.
maybe it's for instance, let's take the ED token as an example. In the first layer, it may prefer expert 2, but and in the second layer, it may prefer expert 10.
Also,
But
it might
they are
prefer a
always
different
preferred
expert. Well, I guess the expert IDs are like arbitrary anyway, right?
Yeah.
So it's kind of like you would expect randomness on that, but still, like
Yeah.
the specificity of the token is like preserved throughout the entire depth of the LLM, basically.
Yes.
Okay. Well, I guess that makes okay, interesting.
Yeah. And are the experts the cluster similar tokens? I think actually, yes. For instance, in expert 0 and expert, in expert 21, we can see all these tokens are very frequently used in the code data. That is the reason why the code data prefer expert 21 so many times, right? And expert 30 and expert 31 has some similar tokens like ed, ing, has, had. So yeah, there are indeed the expert is indeed clustering some token, but not at the high level semantics, just the low level semantics, and also there is no context-based specialization. Specialization is context independent. The next figure here is also very interesting in my opinion. We plot the specialization of different checkpoints during pre-training. We can see all all the checkpoints are at 2,000 billion tokens, 400 billion tokens, 600 billion tokens, 800 billion tokens, and 1 trillion tokens all have the same specialization. I mean, the ED token at this layer has been routed to the expert 30 from very start of the training. So the specialization, the context-independent specialization has been fixed at the very early stage of training, maybe from the warm-up stage. So probably from the warm-up stage. So okay, this is very counterintuitive. We expect the model to change over time, and the routing decision can change on the fly, but actually, unfortunately, not did not. And next figure is also very important in my opinion. This is it's clear that the current routing decision is not that optimal. It's imperfect. How imperfect is it? Is there any real problems? I think the answer is yes. So MoE has a capacity C to set the upper limit of each upper limit of tokens each expert can receive. So uh, in the language models, we generate tokens autoregressively following the sequential order, right? So for the early tokens, it has enough space. It can enter the expert easily. But for the later tokens, if the expert token, the early tokens has fulfilled the expert, and the later token also want to enter the expert, but the tokens in the expert has arrived the upper bound, then the later token has to be dropped to ensure the balanced workload for the efficiency concern. So based on this setting, later tokens are easier to be dropped. In this figure here, we can see later tokens on the pre-training domain, Royal Pajama, the stack, there are fewer tokens to be dropped, even if at the later stage. But for empty batch, which is downstream transport data, a lot of tokens are dropped. Even if we do the supervised fine-tuning on the instruction following and transport data, this issue cannot be elevated, as we show in the red figure. So we call it drop towards the end. This is a buggy issue, and later tokens are not utilizing the MoE's benefits. That is the reason why empty batch, the second round results on empty batch is not that good, and it's even worse than the dense counterpart, because it's kind of the out of domain data for the MoE models.
What do you think is going on around position ID 1000? Why does it jump up and then jump back down, you think?
Okay, you mean the 1,000?
Yeah, well, so the drop rate,
Okay.
goes up and then it drops back down again at about 1,100.
I think the reason is uh, some of the we use the empty batch data to plot this figure, right? And some questions in the empty batch is not that long.
Ah, okay.
Yeah.
But is this I don't fully. I guess I can maybe wait till at the end, but I guess I don't understand why the drop rate would increase with a shorter question necessarily. But basically, you think it's because of some distribution of the data itself that you're evaluating on, basically.
Yeah. In the MoE model, each expert has a number of tokens to be accepted at most. So there is an upper bound of the acceptable tokens.
Right.
And for the early tokens, we can enter the tokens. We can enter the expert anyway, right? No matter how.
Yeah.
We can always enter the expert. But for the later tokens, if the early tokens has fulfilled the expert, it has to be dropped. So later tokens has a higher probability to be dropped.
No, of course, yeah. It was more just like where around 1,000 it goes up and then it drops down again, and like it seems like more tokens are accepted at like 1,200 position ID than they are at like 1,100, for example. This seems a bit strange.
Oh. Okay.
But
okay.
Yeah.
So yeah, I don't have a clear opinion on why this happens it's probably because of the data distribution of the empty batch. If we change a new data set, new countable data set, I think the things would be different. This is a minier case, but I think
was
in
a lot of
general,
just like really hard stuff around position ID 1000. I don't know.
yeah.
Strange. Yeah. Okay. Interesting. Anyway, yeah. Thanks.
Okay, thank you. So we rethink the MoE project. For first, how much code data shall we use? As I suggested before, intuitively we think 30% should be a better results because we observe that when we are using 50% code, the code benchmarks is increasing fast and test benchmark increase very slow. And we are using 20%, the code benchmark increase very slow and the test benchmark increasing fast. So intuitively 30% should be better. And for the tokenizer selection, we used UMT5 tokenizer with a very large vocab, right? And in this table, we compare the compression ratio of UMT5 tokenizer and the Llama tokenizer. The UMT5, the last column, UMT5/Llama, means when tokenizing the same data subset, the ratio of number of tokens generated by UMT5 and Llama. So when the value is larger than 1, it means Llama is better at compressing the text to tokens. And when the UMT5 is when the number is smaller than 1, it means UMT5 is better. So we can see as the multilingual data, for the low resource language, UMT5 is clearly better, but for the code data, it's actually not that good. This is not be expected, but we think it's actually is important insights for the community, and we really need a benchmark to evaluate tokenizer before training and scaling the model up. This is we call this project Tokenizer Arena. Maybe we had some early efforts on that, but maybe someone has built that for the community. I think Meta released a paper about that a few months ago. And also an interesting observation is in this table we can see although we have go through a lot of tokens, but only a very small portion of the vocab of the tokens are activated. So the tokenizer is also sparsely utilized, and the tokenizer utilization is also a long tail distribution. So there may be some space to compress the tokenizer, adapt to tokenizer, and also some better balanced tokenizer usage in the future. And third, more efficient MoE architecture. Based on our observation, the tokenizer has been, the expert selection has been made before the real pre-training stage. The expert specialization has been fixed after warm up, so we can actually remove the router layer, right? Just route the token to the expert area layer. And in this case, we can parallel the FFN layer, the MoE layer and the attention layer, and do the computation on attention layer first, and at the same time do the outward communication and send the tokens to the corresponding expert, so that we can overlap the communication and the computation, and then reduce the overhead of MoE layer, and then make the MoE training more efficient. This is a potential architecture we can use. And for the drop towards the end issue, it is a sparky problem for MoE, right? How can we elevate that? We think the solution can be super straightforward and effective. We can mix the chatbot or conversational instruction following data into the data mixture during warm-up. As we observed just now, load balance is learned during warm-up, and the load balance is learned based on the pre-training data mixture. So then let's just put mix the data into the pre-training warm-up, and then the data, the load balance would be learned based on that kind of data. And and then let's fix the let's fix the load balance and the routing decision in the follow-up training. Then the actual can be greatly elevated. And the timeline of open source MoE models, I think speech transformer is a milestone, and open source it is the earliest open source MoE model. Meta also have a follow up, and our OpenMoE is post ChatGPT stage open source language model. We use a similar setting. We use a different setting as speech transformer and Meta MoE. We use more tokens. We use a slightly different model architecture, decoder-only transformer, and mixture of experts, Llama MoE, DeepSeek MoE, especially for the mixture MoE and DeepSeek MoE are, to be honest, I think they are better trained. They have more high quality tokens, and they are better MoE models. And DeepSeek MoE's paper is also very well written. It's worth it to read. Okay. More thoughts about MoE. So I think MoE is tricky to train. It has load balance problem, training stability problem. It's also data hungry. It's also sensitive to the data diversity. And next important question is, where shall we place the MoE layer? And for OpenMoE and switch transformer, we typically use MoE layer in interleaved manner. I mean, most layers are dense layers, and replace some of the layers by the MoE layer. But for mixture MoE and DeepSeek MoE, they use MoE array layer. Which one is better? I personally suggest the interleaved MoE is better, because MoE includes some communication, introduce a lot of communication overhead, right? The overall communication, and the routing computation. I mean, it would produce many sparse vectors to send the tokens here and there, and also need to compute the load balance loss also. So MoE routing is not that efficient. And using MoE array layer would introduce more overhead. But if we do that in an interleaved manner, we can reduce this overhead significantly. And as suggested in the Vision Transformer MoE paper, the interleaved MoE usually have a better performance than the using MoE array layer. So yeah, that's my insight about where shall we place the MoE there. And also, when shall we use MoE? Training MoE from scratch or dense checkpoint? I think this question, the answer is highly depends on your budget. If you have better data, you want to train the best model. I think you should train from scratch. And if you think, okay, my computation resource is limited, maybe training from dense checkpoint is better. Please note that MoE is more efficient doing training than inference. So using more using more budget at training stage is a more clever and smart decision. Because MoE's efficiency comes from its parallel computation, right? Different experts can do the computation in parallel. And doing inference, when the batch size is very small, many experts are actually idling. So the experts are not fully utilized when the batch size is small doing inference. Then if you have the cost, spend more cost doing the pre-training and makes model better, maybe a smarter choice. And for the routing algorithm, I think 99% of current open source large language model, MoE-based MoE large language model is using token choice routing. But expert choice MoE usually has better performance, especially on computer vision, and also encoder-decoder large language model. The difference is the token choice MoE is given one token, the model select which expert is the best. And for the expert choice MoEs, given a sequence of tokens, expert select the top key tokens, the favorite tokens from the token pool. So the problem here is expert choice MoE need to see all available tokens in parallel. It breaks the autoregressive nature of decoder-only LLM. So there are many. I saw quite a lot of follow-up works on decoder on making expert choice MoE or soft MoE available or compatible to the decoder-only LLM. I think there is a very promising research direction because of the effectiveness of expert MoE routing. But so far, I think most models are token choice. And some takeaways. Strengths, MoE can save the best strength of MoE is it can save the cost. It can save around 50% training cost and less than 50% inference cost. This is based on my personal experience. And if you train your MoE better, have a better set of hyperparameters, you make actual better results than mine. And weakness. MoE is tricky to train, it's more data hungry, it's more sensitive to the data diversity, and also it's more communication expensive. That means it's not that hardware friendly. And the last point is when shall we use MoE? And I think first, knowledge is important. You know, MoE has more trainable parameters than the dense counterpart. More parameters means it can store more knowledge. So for the knowledge intensive tasks, MoE should be more effective than the dense counterpart. And we may need a lot of queries in parallel for startup, for new startup use, we may have only a few users. Then the queries are pretty the number of queries is pretty small. We cannot fully utilize the parallel feature of MoE models, right? But for ChatGPT, there are a huge amount of queries every day, so OpenAI can use MoE. And third, when we have enough data, we see quite a lot of times MoE is more data hungry. This is observed in my previous token crisis paper. It's more data hungry than the dense model, much more data hungry than the dense model. So if you are training a large language model for low resource language, which is greatly data bounded instead of computation bounded, so MoE may not be a good choice. And the last, when we have more time to debug, to be honest, I don't think the current implementation, open source implementation of MoE is good enough. Hugging Face supports mixture very well, but it doesn't support expert parallelism. So it means it's not that efficient to train the model at scale. So when we may need to re-implement some MoE infra from scratch or based on others infra, and things may become buggy and not that flexible. So yeah, if you want to onboard MoE, maybe you need to prepare some time. Yeah. So yeah, thank you for listening. That's all for my presentation.
Amazing. Well, thank you so much. Let's give a big round of applause to Full Draw, everybody. Okay, so we can open up to some questions. I certainly have some, but we've already got one coming through. And I don't know if that was an applause you intended, Vat, or is that a question?
No, it's a question.
Yeah.
So if I'm intuitively thinking about it correctly, MoE models kind of only allow for a subset of the total parameters to be activated. And this is kind of like based off of the routing where you kind of select an expert for that specific case, whether or not you use that expert. I'm assuming this would introduce some sparsity, which probably leads to like more memory consumption. And so like would more recent hardwares also kind of improve the relevancy of MoE, for instance, because they could deal with the sparsity?
Okay.
I guess the
yeah.
point being that there's some dormant experts that need to be sat around in memory that might not be being used, and whether and
Yeah,
whether like, new
exactly.
hardware can kind of deal with those dormant experts in a better way.
I think mm, first, I think there is no clear uh, solution for this problem. Just to use the balanced load balance routing algorithm, load balance loss to make the workload as balanced as possible. But intuitively, I think one possible solution is if this expert is much more frequently used, we can make two copies of this expert, right? During the deployment, make two copies of this expert. And if this expert is not that fully used, we can put two experts into a single GPU instead of distribute each expert on one single GPU also. So there may be some brute force solutions for this problem, but for the elegant solution, I didn't see that so far. I haven't seen that so far yet.
Got it.
Makes sense.
Makes sense. Thanks for answering.
Any other questions in the room at all? Okay, well, I can come with one, which is just to say, maybe exposing my lack of knowledge about exactly how the training works. But I guess during training of mixture of experts, you could, for example, do a soft loss where you take the probabilities and then you do the weighted sum. I actually saw that in one of the slides you had earlier, and you kind of back propagate the loss through all of the experts, and then in a way, kind of each expert gives their opinion, and you like weight the expert opinions together based on the routing probabilities. Or you could kind of do like a hard non-differentiable selection, pass that through during the forward pass, and then back propagate through the individual expert. Are both of these approaches done, or is it always one of them? Like, I didn't fully follow that.
Okay, this is a very good question. Actually, you are approaching the hardcore point of MoE design. Let me show this figure. Okay, I think the case is when doing routing for each token, we first compute a softmax score as kind of the probability and select the top one expert,
Yeah.
top one expert, and then send based on the top one selection, send the token to the corresponding expert directly. And after computation on the expert, we multiply the score, the probability, onto the output
I got
token
it.
so that it can make the whole process differentiable and can be trained by the backpropagation.
Got it. So it's a bit like max pooling. I think that's a similar approach in computer vision, where you have like as a an approach to kind of do image reduction instead of doing a strided convolution. There's max pool, and I think even in that case you would multiply it by the probability, for example. But yeah,
Yeah. I think this
you
trick.
don't sum them. Are there any points where they? I guess you wouldn't get the benefit of mixture of experts then, because if you trained it where you did a weighted sum of all of the experts, you then need all of them during inference. So that wouldn't be so great because they would like learn to work together on a token by token basis. Is there any kind of research in this direction at all, or not so much?
You mean the soft MoE routing?
Yeah, exactly. Is that so?
Yeah,
I guess it has a
yes.
name then. So that's something that people
Yes,
do.
I think soft MoE is very effective. But so first, sending tokens to every expert would break the sparseness.
No, exactly. So you
Sparseness.
lose the inference improvements in a way and the
Yeah,
parallelization improvements, but I guess it
yeah,
might
yeah,
be
yeah.
better.
There are
It might
some
be more
tricks.
computationally efficient, I guess.
Yeah, there are some tricks. You can follow one paper named as Soft MoE from Google Brain, I think last year. I really like that paper. Uh, it can make the uh, make the MoE routing more differentiable and more stable, and also can maybe actually maybe that is a game-changing routing also. Yeah.
But I guess I would imagine it with soft NOE, it then wouldn't work well if you turned it after training to hard NOE. I guess it relies on multiple experts to get good performance. If you trained it as a soft NOE and then you did and then you clipped it and just did an hard max, that would kind of be poorly performing, I guess.
Okay.
I presume that when you train soft MoE, you then need all of the experts join inference as well, basically, is correct, right?
Not actually. You can when using soft MoE, you can compress the number of tokens.
Right.
Yeah, you can compress the number of tokens. The MoEs, each expert can have a query and apply the attention on the token representation. So it actually use fewer tokens are feeding to each expert. So the computation cost is still reduced.
Yeah, yeah. Okay, that makes sense.
Yeah, something like perceiver, cross attention.
Okay.
Oh, sorry, I can't hear you clearly.
Oh, sorry. Oh, you just asked me. So I was just going to say I have one more question, which is basically, this might be, no, I think I'm going to the panel. Yeah, then the question is just like,
Dan, there's probably something wrong with the mic.
oh, you not hear me clearly?
It's kind of not clear.
Oh,
Yeah, it sounds a bit filtered.
okay. I'm not sure what's going on here. And then, yes, okay. Okay. Can you just say now?
Nope.
No, it's still
Still,
unclear.
I mean, we can hear you, but it's not
Yeah.
audible. Nope.
Nope.
Now is it better?
Yeah, it's audible.
Yeah.
Yeah.
Now it's my webcam. Okay, I don't know what's going on. My mic's going crazy today. Okay, sorry. So final question for me is just, do you think there is any semantic meaning at all to the experts? Obviously, what you find is that basically very early on in training, they get locked into one token, and then they kind of can't move from that, which kind of makes sense because with it not being soft MoE, you kind of have this hard thing where like early on in training, based on the random initialized weights, you start to send tokens to certain experts because what else is there to kind of condition on? It's not learned anything yet anyway. So you kind of get each of the tokens kind of locked into their particular experts with a routing function. And then they kind of can't escape that with the gradients, I guess, because you just kind of keep increasing the probabilities or something. But, and obviously there's no then semantic differentiation in terms of tasks like Python or JavaScript or whatever. But I wonder, yeah, I wonder whether you believe, therefore, that mixture of experts is only about efficient distributed computation, and that effectively kind of, instead of having one big matrix multiplication, having smaller matrices that learn how to deal with certain tokens is just more computationally efficient, and that's it? Or do you think there is like some deeper kind of generation of expertise that might be happening that just doesn't make sense to us humans on a semantic level? You know, do you think there might be some interesting clustering that emerges in the prompt space with the experts, or do you believe it's just token specialization, computational efficiency, and nothing more is happening?
I think it's happening something. It's still happening something, right? There are some basic semantic clustering, token ID clustering. So
Yeah.
at least it's learning something.
Yeah.
But I think so for the current OpenMoE is the training strategy is absolutely suboptimal.
Yeah.
And the early routing learning and the context-independent routing may be caused by the load balance loss.
Yeah.
You know, the load balance is much easier to make next token. So the
Yeah.
model would be lazy and just learn the balance routing first, and then
And the
based
load
on
balance loss means that it needs to use all of the routers somewhat symmetrically, like evenly.
Yes. Unified token distribution.
Yeah.
Unified expert utilization. You learn that first, and then make that fixed, and then make that first, and then to do the semantic learning. So this order is problematic. We should learn these two abilities in parallel, and maybe even learn the routing decisions later. So this is a algorithm problem. And need some more research effort on this topic. Maybe OpenAI has solved this. I guess they probably have solved this, but we don't know how.
Probably.
Yeah.
Yeah, makes sense. No, I think obviously soft MoE is an interesting direction in that respect, where you kind of don't lose out on the gradients of your other experts and your other routing probabilities too early on in training. But yeah, I guess yeah, I guess yeah.
Actually added some random noise to encourage the model to explore more answers, but it seems it didn't work.
It feels like the days of kind of reinforcement learning again. Like, how do you get Q learning to work? It's like adding random noise to the policy or something. I guess these kind of very discrete things are often quite brittle when you kind of lock yourself into one area of the exploration space, and it has that flavor a little bit as well.
Yeah, maybe the noise is not strong enough, and also the noise. So the token was sent to a new expert. The expert said, "Oh, I didn't say that it's out of distribution token," and kick it back to the original expert, and then it doesn't work at all.
I imagine, I don't know, but I would guess that if you did soft MoE, the load balancing loss eventually might be less necessary, because surely the global optimum is to utilize all of them, right? So
yeah, but soft MoE cannot be applied to autoregressive language modeling directly, because it needs to solve the all tokens to compute the soft score. And there needs some tricks. For instance, groups the tokens into many groups the candidate tokens, and then compute the soft token merging within the group. Maybe some other tricks are required.
Yeah, it makes sense. Super fascinating. Anyway, I could talk all day, but I will let you get back to all of your hard work. I realized, I checked the YouTube video, I realized that we didn't, the beginning was cut because of the technical difficulties we had, so I never gave you an intro. I'm going to quickly do it on an outro, because I feel as though everybody that joins us should have, should have the background. So, well, first of all, it was really, really great to have you. Let's give a quick round of applause again, everybody in the room. It was really, really a great talk. And just for context, because we were cut off at the beginning, Fuzhao Xue is a PhD candidate of HPC AI under the supervision of Professor Yang Yu at the National University of Singapore. He's got an MH degree from NTU, where he got outstanding academic performance with a perfect GPA of 5 out of 5, which is something that I think all of us wish we had. Certainly I do. Anyway, yeah, and his kind of obviously doing a lot of work in machine learning, NLP, and high performance computing. I just thought I'd get that in at the end of the video, given that we cut it at the start. But again, it was a real honor to have you with us. Of course, I'm sure you're going to keep dropping bombshells in the mixture of experts space, and we'll be very lucky to have you join us again when you drop, if and when you drop the next one. But yeah, thank you very much for joining us today. It was great.
Yeah, thank you, Daniel. Yeah, thank you all.
Awesome. Thanks a lot. Have a good day, everybody. See you guys next week.
Bye.
Bye-bye, everybody.
Bye.